So my name is Gorjan, and today with my close colleague Gjorgjina, we will be presenting about rule-based named entity recognition systems for food, and how that further translates into, or rather evolves into corpus-based food named entity recognition systems. As Thomas introduced us, thank you very much. We come from the Jožef Stefan Institute, and with this I begin. So the first half of this presentation will be related to rule-based named entity recognition systems for recognizing food entities in text. So a brief motivation as to why this is needed and why this is an important field in natural language processing in the domain of food and nutrition. In front of you on the slide, you can see the knowledge pyramid. This knowledge pyramid represents the steps from the steps that data evolves through while it reaches a certain specific level of quote-unquote usefulness. So in this case, we can see that we have 4 levels, which are data, information, knowledge, and wisdom. So the data is the most raw and unstructured and unprocessed form of data that is commonly found in everyday scenarios. After having some specific structured information or some structure added to this data, we get information. Then that further evolves to knowledge, which basically includes some sort of context and some sort of symbolism in that information. And finally, we achieve the highest level wisdom. In many biomedical domains and in many biomedical applications, this data is already processed and is already in such a way that can be useful in systems that deal with knowledge. However, in the domain of food, we are still at the level of data. So in the domain of food, we still are in the process of having this data from all various sources and all different types of sources, where we still can't make some sense or draw any conclusions or find patterns in the actual data. In order to get to the next step, so in order to evolve into this information layer of this pyramid, this data needs to be collected and structured from unstructured sources. So what is formal information extraction? The process of extracting automatically or semi-automatically information from unstructured data is called information extraction. In this case, we'll be specifically speaking about text. So in this case, all information, all the food data that we need to structure and extract is in the form of free written text. A subfield of this information extraction task is named entity recognition, which basically is exactly identification and classification of predefined concepts from a domain of interest from this unstructured data. So there exist multiple different types of named entity recognition systems, which are all based on the theory on which they are built. So some of them are just based on dictionary lookups, hence dictionary-based methods. Some are based on rules that incorporate some sort of information of computational linguistics, semantic, or whichever type of information might be available for this domain, and hence are rule-based systems. Further, we have corpus-based systems, which Gjorgjina will present after I conclude, which require some sort of corpus annotated from this domain in order to be trained. And finally, one other interesting type of named entity recognition systems are methods based on active learning, which basically query the user constantly and have this sort of ping pong between the user and the system that is learning. So I'm going to specifically focus on rule-based methods now. The first one I would like to introduce is Dr. NER, which is rule-based named entity recognition systems for evidence-based dietary recommendations. It is basically split in three different steps. So these steps have to do with how the actual text is processed. At the beginning, we have this pre-processing step where some quote-unquote cleaning of the data and some specific manipulation of the raw text is performed, upon which the actual data is quote-unquote hidden. So here we would have something like chunking or just splitting the words and having it in a much cleaner state than it would be otherwise. The next step has to do with working now towards constructing this whole methodology, where we have these dictionaries from which we build matrices, which have an analogous matrix, which is from the entities. So now in this specific step, one of the interesting aspect is we find part-of-speech tags, so POS tagging. And then we have the final step where we combine all of these and actually identify and extract the whole segment of interest in this raw text. If we look at this pipeline, we observe that from the beginning, we have a simple raw text as input, so nothing more than just free written text. And at the end, we get this structured output, which gives us recommendations, the target demography, and as well, of course, the food entity or nutrition-based dietary recommendation that is extracted. So let's look at some of the results from this. You can see the table on the slide, which has a couple of different interesting fields. The first one is the actual text or the actual segment in which this information is contained. So after this process, we have these segments in which we can say for certain that in this segment, we have some information that is worth extracting. So at the left, in the first column, you can see this raw text. And then moving on, we have a group, which is the target demography in this case, which in and of itself is an entity of interest. Even though it is not specifically from the domain of food, it is very closely related to the application, and thus we need to have it extracted. If you can see, we have an example where one target demography is babies. Furthermore, the next column is action, where we have what specifically is done with these entities. So not only do we now have the entities extracted, but we have some sort of relation between the entity and the actual target demography. Finally, or rather most importantly, it's the actual food segment that is extracted. In this case, is the whole segment from beginning to end, which has all this information, all this data regarding food and nutrition, which specifically is acted upon. Closely related to this column is the second column, which is nutrients, which is basically just another entity of interest in the domain. And finally, we have the quantity or unit. So with this, we have the whole processed, or rather the whole unprocessed text processed, where we extract all of these specific entities of interest, and then we have all of these final structured fields filled in. So now we're not looking at raw text, we're looking at something that has structure and that can be parsed, at least in some part, automatically. So when evaluating this, of course, we stick with the classic true positives, false negative scheme, which is one of the, or rather the standard when evaluating such classification or rather named entity recognition methods. In this case, true positives are the thing we want to optimize, so the thing we want to maximize. False positives and false negatives are entities which are either recognized as as important and are not. So food that is not food, or rather not food that is food. Entities that are not recognized but should be recognized from this text. So as we can see, this methodology provides very promising, very robust results, having a very high number of true positives for food, nutrients, as well as quantity, as opposed to the other two types of matches. So with this, the evaluation is performed on the text corpora and on the different scientific publications on which it is run on. The next methodology I would like to present is Foodie, which is a rule-based food named entity recognition method. Much like the previous one, with one major difference. This method outlines or rather extracts all of these different entities separately. So not only do we have now the whole segment in which these entities occur, we have the entities themselves as a standalone concept. So much like, again, the previous methodology, which is based on Boolean algebra, here we have some rule engine which includes Boolean algebra rules, which have this computational linguistic information inside it and this actual semantic information inside it. So the first step is, of course, pre-processing, where we just clean up the text and have some sort of specific kinks in the text sorted out. Following, we have the part-of-speech tagging and post-processing of this text set. At this step, we use some sort of ensemble from different part-of-speech taggers, so we have a more robust result. Moving on, we have semantic annotations of the food token in the text, of course. This means that we have some sort of semantic information introduced in the system, which is further used to recognize whether this is or is not a specific food of interest. Then we have the actual named entity recognition. This is the first step where the actual rule engine lies. And finally, semantic annotation, which deals with concatenating and having all of these semantic tags in this concept joined together and not have them separately as different tags, because it's then again, it's at the end of the day the same concept. So again, we can see that we start from raw text, in this case recipes, unstructured, written by anyone, data collected from various sources, which have no structure. And at the end, we get a specific structured output with annotated food entities. This is an example of how this looks. So the whole screen depicts one recipe, and each of these green squares is one entity. What's interesting to note here is that we have entities that consist of multiple tokens, so entities that consist of multiple words. This means that not only do we have single token entities, we have multiple token entities which have semantic meaning in each word of that chunk, of that concept. As you can see, we have different types of morphological structures. So we have different types of words like nouns, adverbs, verbs, and etc. And each of them has a semantic connotation to it, meaning that it is important to be extracted. One major upside of this methodology is that it is able to recognize these words and these important semantic carriers of in the concept without having any prior knowledge and any prior corpus built upon them, purely based on these semantic rules and these computational linguistics rules. The evaluation was performed manually, which means that human experts were tasked with checking each of the outputs from the methodology and checking them against their, of course, subject matter expertise, and then tagging each of these entities as true, false, as is in the previous example, true positives, false positives, and false negatives, with one important addition where we have this type of match called partial, where we have this entity of interest, but it's not captured wholly. So we have one word that is, or at least one word that is missing or superfluous in the actual concept that is extracted. So for example, if we have green onions and only extract onions, that is a partial type of match. We don't have all of these semantic carriers in the concept recognized. Having that said, the evaluation showed that we have very robust results and that we have significant gain by using this methodology. And on top of just computing all of these matches, we computed as well the fairly known precision sensitivity and F1 score, which all target various aspects, but taking the F1 score as the de facto standard for evaluating these types of methodologies, we can see that it performs very well indeed, where an ideal score would be 1. So this is a very close score and has different upsides to using the methodology when wanting to extract some specific entities and not having it as an unstructured text. So with this, I conclude my part of the presentation and give floor to Gjorgjina so she can begin hers.
Right, so I will now go on to present the corpus-based approaches to named entity recognition. So in order to obtain good results, the dictionary-based methods that Gorjan mentioned require extensive dictionaries, which will contain several possible alternations of an entity's name. And if a specific alternation is not in the dictionary, the method will fail to find the entity from the text. Also, the dictionary-based approaches do not take into account the context of the words. So rule-based methods can do this to some extent. However, establishing the rules for every context is practically sort of infeasible and requires a lot of manual work to construct the rules. Corpus-based approaches solve this by training a supervised model using an annotated corpus, and they are capable of taking into account the context. The most common approaches involve the use of support vector machines, hidden Markov models, maximum entropy Markov models, and conditional random fields. And these methods learn complex features of language and eliminate the need for manual feature engineering by domain experts. So they are also more robust since they aren't affected by terminological resources and manually created rules. So the models that I will present as part of this presentation are trained on the food-based corpus, which is annotated for the existence of food entities in recipes collected from the All Recipes website. These recipes were first annotated by Foodie, which is the second rule-based method that Gorjan presented. And then 1,000 of these recipes were checked by human experts. That a golden standard was created on which we can reliably train supervised learning methods. Since we have this annotated entities, we can now map the named entity recognition problem to a classification problem where the task of identifying food entities is sort of treated as a classification problem where the classes are the tags from the inside-outside beginning tagging scheme. So we need to assign one of these tags inside, outside our beginning to each word in the recipe. So here in the example, we have the sentence, place the sun-dried tomatoes in the water. So in this case, the food entities are sun-dried tomatoes and water. So sun-dried and water get assigned B tags since they are the beginning of the food entities. Tomatoes get assigned an I tag since it is inside a food entity, and all of the other words in the sentence get assigned O tags. So the first method that I will present is called butter, and this stands for bidirectional LSTM for food named entity recognition. And this is the first corpus-based named entity recognition method in the food domain. It is based on conditional random fields and bidirectional long short-term memory. And as I mentioned, it is trained on the food-based corpus. So here we use three pre-trained word representation models to represent the text into numerical format, which is expected by the neural network model. So we use the GLAV, Word2Vec, and FastTech pre-trained models, and we also consider training our own embeddings. And the method that uses these embeddings is referred to as the lexical model. So because the pre-trained word representation models can only represent words that are present in their vocabularies, we also introduce a pre-processing method for handling the words that are not present in their vocabularies or the out-of-vocabulary words. And we also consider lemmatization for the lexical model. So as I mentioned, we use BLSTM and conditional random fields model architecture, which is a standard for named entity recognition and has also been extensively used in the biomedical domain. And we also consider how supplementing the word representation obtained by using the pre-trained models or the lexical models with additional character embeddings is going to affect the performance. So these character embeddings are generated using an LSTM and are concatenated with the word embeddings and sent to a sequence of BLSTMs and conditional random fields, which at the end produce a probability of each word belonging to one of the classes of the inside-outside beginning scheme. So the models are evaluated using 5-fold cross-validation and report the macro average F1 scores. So we can see that all of the proposed models obtain an F1 score of at least 0.89. And the best one is the lexical lemmatized model without character embeddings, which obtains an F1 macro score of 0.94. Apart from using these context-free word representation models, which are slowly becoming sort of outdated in the field of natural language processing, we also consider the transformer models, or specifically fine-tuning of BERT and BioBERT models for the named entity recognition task. So FoodNer is the second corpus-based model trained on the food-based corpus. And the difference between Butter and FoodNer is the fact that Butter can only distinguish food from non-food entities, while FoodNer is also capable of classifying these food entities into food groups from the Hansard corpus and the Foodon and SNOMED city ontologies. So the initial results are pretty encouraging. So the model achieves an average F1 macro score of 0.93 to 0.94, which is similar to the performance of the best Butter models. And on the multi-class classification task, it achieves F1 macro scores of 0.73 to 0.78. So to sum up, as part of this presentation, we have introduced two rule-based and two corpus-based models. So Dr. Ner and Foodie are the rule-based models, while Butter is the first corpus-based named entity recognition model, and FoodNer is the second one, which also supports multi-class classification into various food groups. So that is about it from our part. We'll look forward to answering any questions.
Okay, thank you, Gorjan and Gjorgjina, for the nice presentation. So actually, you show us that using such kind of name entity recognition and information extraction methods, we are able to extract information that are about like dietary records, what people are consuming each day. So this information can be further reused for some analysis, which is, and also, for example, mapping food consumption with food composition data. I cannot see questions in the question and answers, but actually I have two questions and maybe I can ask them. And if you have some questions, please feel free to write them in the question and answer part in the platform. So my first question is actually, because you said that first Gorjan presented nicely about the rule-based approaches, and then Gjorgjina she presented about the corpus-based approaches, and she said that there is multi-class classification. If I understand correctly, the first part is only binary classification. Is it food and non-food entity? And then the second one is actually multi-class, which is trying to distinguish between food groups. My question is actually, because you said that this is trained on food-based. If food-based supported different semantic resources to train corpus or to train different name entity recognition, because, for example, you can distinguish between food groups, but actually these tags are only for one resource, or it can be used for different resources.
So the initial way the food-based corpus was built, sorry, I'm hearing feedback. Okay, that's fine. So the initial way food-based corpus was built was by using this Foodie method and then manually annotating the rest of the recipes. We're using the Hansard corpus as the base semantic resource in that methodology. But then that's further extended with another methodology called Foodontomap, which has multiple different ontologies taken from the bioportal, such as Foodon, SNOMED city, OntoFoods, Mesh, and different other ontologies that have food. And by using their named entity recognition system, we can link this Hansard-based food-based dataset with these different datasets. So in essence, at the beginning, we have a binary classification model where we just extract the food. Then we have the next step where we have the Hansard tag. So it's, in this case, again, multi-label, multi-class classification, where each entity can have multiple labels. And at the end, we link this with different ontologies where we have the same multi-class, multi-label problem, but now we are linking it with different named entity recognition systems. But this is a separate methodology, but it is based heavily on Foodie.
Gorjan, and maybe one more question is about because of these sustainability problems which are currently and reusing like resources that are developed, if you have an opportunity to choose between rule-based and corpus-based models, for example, for which one you will decide?
So
if I would have to choose, the first option is using rule-based, because if you don't have a data set, you can't make the corpus-based. If you have the data set, then the corpus-based is the better way to go, in my opinion. But if you have no point of reference and nothing prior done in this field, you need to work with rule-based systems because you just don't have the data.
Okay.
It's manually annotated at the end.
Okay, thank you very much. And thank you again for the nice presentation.